Hey guys, welcome to this video on proofs for sequences and series. So what I've got here is just a series or a sequence here of numbers, so 1 to the power of 2, 2 to the power of 2, etc. up to n to the power of 2. And that is equal to this funny little symbol here, which actually reads as the sum from I equals 1, which is the bottom part here, to n of I squared. So from I being 1, I being 2, I being 3, etc., all the way up to n. And what we want to prove is that this sequence here is equal to n multiplied by n plus 1 multiplied by 2n plus 1 divided by 6 for all integers or all positive integers of n. So the way we're going to do this is again by mathematical induction. I'm going to split it into two parts, so part 1 and part 2. But first we need to go, or say that all of this part here is also equal to Pn. So let's go with part 1 to start with. So if we've got n being equal to 1, and we're going to call this the left hand side, and this here is going to be our right hand side, because I'm going to refer to those in this part. So if n is equal to 1, then it's just 1 squared, which is just equal to 1. If we look over here, we've got, if we look over to the right hand side, when n is equal to 1, it's 1 multiplied by 2 multiplied by 3. So 1 times 2 times 3 was just equal to 6. 6 divided by 6 also equals 1. So we could say the right hand side is equal to 1. And let's put in here left hand side. So therefore we could say that P1 is true. But now what we want to do is show it for other cases. So that's why we're going to go to 2. So we're going to go if proposition k is true for all positive integers of k, then the sum is going to be 1 squared plus 2 squared plus 3 squared plus all the way up to k squared is going to be equal to k plus 1, 2k plus 1 divided by 6. We're also going to take this the next step further and make it 1 squared plus 2 squared plus 3 squared, not squared, not cubed, all the way up to k squared plus k plus 1 squared, and that's giving us that bit there. We're also going to make it equal to k plus 1, 2k plus 1 divided by 6 plus k plus 1 squared. And what we can do with this is multiply this by 6 on 6, which essentially we know is just 1, and that will give us the k plus 1 squared over 6, which will make it easier to add onto the rest of it. So this will become, let's keep going down here, k plus 1, 2k plus 1 plus 6k plus 1 squared, all divided by 6. We can see that we've got a common factor of k plus 1, so we can take that out the front. Plus 1. I'm going to use square brackets here because there's going to be a lot. K 2k plus 1 plus 6k plus 1. And obviously that's not squared anymore because we've taken the common factor of k out. Now if we expand what's in our square brackets out, it's going to end up being something that looks a little bit like this. And I'm going to move up here. So this 2k squared plus 7k plus 6 can be factorized down, and we can actually split it into small common factors. So let's go up here. If you're not sure on how to factorize this, you could use the AC or AC equals method. You could actually split it out to make everything to be k plus 1. So we've got k plus 1 out the front here, because that's what we're aiming for. We're trying to look for all these k plus 1s that we get. Then we're going to have k plus 1 plus 1. I'm going to put some square brackets around that one. Then we're going to, so that's splitting the k plus 2, it's k plus 1 plus 1. Then we're going to split that k plus 2 up to make it look like the 2n plus 1. So we're going to have 2k plus 1 plus 1. Now we can see that we've got this, wherever we've got n now on this last final bit here, we've actually got k plus 1, and that's what we were trying to get to. So once we've gotten to that step, we can then go, well, since p1 is true, and pk plus 1 is true, because we've just found that, so that's that bit there. Whenever pk is true, that means, therefore, Pn is true for all integers of n, or all positive integers of n. And that's our principle of mathematical induction. So we could then go through and find p of 100, and we'll just plug it straight into the formula that we've got, which is our right hand side formula above. So that's really the basis of going through sequences and series. It's just the same thing, just prove it by mathematical induction. Go through again and again and again, and you'll get your answer. So that's all I wanted to go through in this video. If you've got any comments, please let me know. Otherwise, thanks for watching, and we'll see you next time.